Swayam Prabha. Digital India. Educated India.
Yesterday we were looking at the different chains of the polymers, different kinds of polymers with different molecular configurations. We will continue that discussion and see the effect on material properties. For example, we saw that when we have a long chain, we have different kinds of possibilities. One is the atom rotating about this, maintaining this bond angle constant. Similarly, you have another macromolecule where there is a chain which is bending, which has got several bends, and then the movement of this molecule of this atom is not as free as it should have as it should be. But then so there is some hindrance over here as a result of the bending of the molecular chain. Similarly, here it is twisted as well, and therefore particularly when you have coiling, bending, twisting, etc., the movements are not as free as you have them here. So when you have a macro chain something like this, then when you pull the chain, what you are doing essentially is you are unbending the bent chain, or uncoiling the bent chain, or untwisting the bent chain. So if I am pulling a polymer, for example, I am pulling a nylon rope or something like that, I am pulling a nylon thread, then these chains tend to get straightened out. So here there are a number of bends which tend to get become straight, the twisting gets uncoiled. So basically the straightening out of the chain manifests itself in extension of the polymer strand or polymer thread. So here what we see is that how polymer chain shape is influenced by positioning of backbone carbon atoms. So here the chain shape gets influenced significantly by the positioning of the backbone carbon atoms. Here you see a bent chain, here you see a twisted chain, and here it's a mixture of everything. We have seen that there are extensive van der Waals bonds which are prevalent between two chains. Two linear chains also have their own share of attraction and repulsion, and so we have different mechanical behavior as a result of this. The branched chain, as in case of LDPE, low density polyethylene, are the outcome of a number of chains or number of branches being formed in a single chain, and when these branches interact, again they prevent the two chains coming together, and that is the source of strength in case of LDPE. So we talk about HDPE, polystyrene, PMMA, etc., where these chains are responsible for generating the strength that we see. So the ease of sliding reduces the strength, or basically ease of sliding can be seen as a deformability of the material. Ease of uncoiling, ease of unbending results in a strain at a lower force, and that's why we will find that the polymer is then relatively amenable to deformation. But then most of the deformation what I am talking about is fully recoverable. So although it is tangible, although it is significantly large in magnitude, it is recovered. I compared these chains with springs yesterday, but then there is so the macroscopic difference or the macroscopic deformation of the spring, right? The spring deforms on a very macroscopic scale, and then that macroscopic deformation can be retrieved. So these chains behave exactly the same way as multiple springs, and so when you have these branches, you have springs which are branched out. So there is a good resemblance between how a collection of springs would behave and how this will behave. Now when you subject a material to compression or elongation, what you are doing is you are elongating a bunch of molecular chains. You are elongating or you are compressing together a bunch of polymer chains. Similarly, when you are doing extrusion, you circumferentially compress the polymer chains, try to bring them together as well as elongate them in the direction of extrusion. So all this results in alignment of the chains, their unentanglement, and then you have uncoiling, unbending of the chains, and then the chains tend to be more or less parallel. But then when they are brought together, as you see here, there will be a resistance for the chains to come together as a result of the hydrogen atoms preventing the other chain from coming together, and therefore you need a greater amount of force to force these chains together, and therefore once the force gets removed, the deformation gets recovered, meaning that you are trying to force these chains together by an extrusion tool or some tool which you were using for deforming the chain or deforming the workpiece, and then when the force is removed, the entire deformation gets recovered. So this elastic deformation is the one that gets recovered fully. So that is the reason I told you yesterday that the workpiece tends to swell appreciably. In metals, the elastic strains recoverable are to the tune of 0.2%, which is an extremely small amount, and it is irrespective of how much deformation you have. For an undeformed material, it is 0.2%, and for deformed material, of course, it will depend upon the stress from which the unloading has taken place. Now here what happens is the extent of deformation is completely recovered, and this recovery takes place immediately after the load is released, and so you have the component returning to its or tending to return to its original shape, more or less the original original diameter tends to get recovered. Yes, there is a change in the layout of the chains, but you have alignment of the chains, but then there is significant amount of swelling of the workpiece when it comes out of the extrusion die. Now we were talking about molecular configurations, which is called as stereoisomerism. So one configuration is an isotactic configuration where these functional groups are, as you see here, are on the same side of the carbon atom. So you have these carbon atoms, and these are on the same side of the carbon atom, and what you see here is that they are on the left hand side of the hydrogen atom, and then what you can infer from the solid wedges is that they are bonds projecting out of the plane of the screen, and the dashed ones represent the bonds going into the screen. So these are coming out of the screen, and these are going into the screen. So you have this consistently with the functional groups over here. As opposed to that, a tactic configuration, you have these functional groups on the left hand side here and on the right hand side over there. So they can appear either on the left hand side or on the right hand side in a tactic configuration. So there is no systematic way of arranging these functional groups R. If you look at syndiotactic configuration, you have the configuration in which there is again some symmetry that is maintained, but then two functional groups tend to come together here as you see, and so but then there is some symmetry that is maintained. So you have if you take this, then you have R, and in between you have 2H. Here you have R and R, between that you have 2H. So similarly you will have R and then 2H and again R. So this is called as syndiotactic configuration, whereas atactic configuration you cannot identify such kind of definite patterns in which the functional groups are arranged with respect to the carbon atoms and the neighboring hydrogen atom. Geometric isomerism is another issue here. So in this repeat unit, which is shown over here, it is an isoprene repeat unit, and the methyl group and hydrogen on the same side of the double bond gives us the cis isoprene. So this methyl group and hydrogen. So this was R, as we saw in the previous case. So this can be treated as R, and this is H. Similarly, so now here you have CH3, that is R, and hydrogen in opposite sides of the carbon atom. So it is not just a way of writing things, it immediately influences the properties. So these two isomers are not going to have the same properties, they are not the same. So from that point of view, although the ingredients are the same, the functional groups are the same, the CH2 are the same, even the two CH2 groups are the same, still you cannot find same properties in these two. So that is why it is this is called as trans polyisoprene. So this will give trans polyisoprene, where CH3 and H are on the opposite sides, whereas here it is cis polyisoprene, where the two are on the same side. One point to note here is that conversion of trans to cis or vice versa is not possible by a simple chain bond rotation, because the chain double bond is extremely rigid. So what it means is that you can't just rotate this carbon atom by say 180 degrees, and then so this bond cannot be rotated by 180 degrees and hydrogen brought at the top to make it cis polyisoprene. That is because this double bond here is extremely rigid, it doesn't rotate very easily. Had it been a single bond, probably it would have been possible to rotate, but a double bond is extremely rigid. And just like metals, in order to improve properties, one can add what is called as copolymers. So just like you add alloying elements to improve the properties or enhance the properties of the base metal, you add copolymers to enhance the properties of the host polymer or polymer chain. So for example, you have this as a single chain, and then you have this random alternating or block or graft type of arrangement here. So styrene butadiene rubber is a random copolymer, so it's a random copolymer. Nitrile rubber, which is combination of acrylonitrile and butadiene. So these are this is a random copolymer. So styrene butadiene rubber is random copolymer. Nitrile rubber contain these two, and this is also random copolymer, and these are used for making gasoline hoses, our gas pipes which we change from time to time are made from these kinds of rubbers. So these are again random in nature. So these copolymers are random, alternating, block and graft. Impact modified polystyrene is a block copolymer which contains styrene and butadiene. So you have this as a so you have blocks here. So you see that this is a block. So you see the atoms of one color with another color. So one block of atoms alternates with another block of atoms. Here it is third block of atoms, fourth block of atoms. So basically one species of atoms in a block alternate with another species of the block. So, you let us say you have styrene and butadiene. So, this could be styrene, butadiene and so on. Here you have alternating. So, each one of them is alternating with respect to each other. So, you have these dots which are so if you take a polymer chain, then these styrene, butadiene, they arrange themselves in alternate locations, whereas random means that there is no sequence, there is no specific sequence. So, styrene butadiene rubber is a random copolymer because the styrene and butadiene, they are not arranged in any specific order as such. Had they been arranged this way, they would have been alternating. Okay, had they been arranged this way, they would have been block styrene and butadiene. Okay, so that's the difference. I mean, the application therefore change depending on the kind of molecular chain you have, whether it is random, whether it is alternating, or whether it is block. So you have repeat unit name acrylonitrile. This is the structure of acrylonitrile, and the overall average weight is a fraction of. So if you take a copolymer, then the average molecular weight is a linear combination of the fraction of the copolymer into its molecular weight. So the mole fraction of the molecular weight of repeat unit J in the polymer chain is will give us the average mass of the or molecular weight of the overall polymer. Now I was telling you that some polymers are crystalline, and just like our crystal structures, the polymer chains arrange themselves in such a way that it gives an impression, or it creates an impression of regular arrangement of atoms, right. So polymer crystallinity is the packing of molecular chains to produce an ordered atomic array, right. So ordered atomic array is produced by appropriate coiling of these chains. So polymer chains are the same, but then the way they are arranged results in these ordered atomic array. So the chain molecules extend beyond the unit cell. The molecular substances having small molecules like water and methane are either totally crystalline as solids or totally amorphous as liquids. So whereas with large molecules, with polymer macromolecules, it is not possible to have the entire polymer crystalline. So you have polymer molecules are partially crystalline. Crystalline regions are dispersed among amorphous material. Twisting, kinking and coiling of the chain prevents strict ordering of every segment of every chain. So that is precisely the problem with these polymer chains. In a macromolecule which you saw earlier, if there is lot of twisting, coiling and this kind of an arrangement, it is extremely difficult to get an orderly arrangement of atoms in the entire polymeric chain. However, you will have some local regions where the arrangement can be of a regular nature, but otherwise it is difficult to have an ordered atomic array throughout the entire chain, and particularly when you have macromolecules. Yesterday we did a small calculation and found that the monomer gets repeated 338 times. Now over such a large amount of repetition, it is difficult to it might be difficult to get an ordered atomic array and crystallinity in the macromolecule. So you can have crystallinity or order arrangement of atoms in a very local domain. A small volume can be seen as orderly arranged, but the outside that, or you can have several such small volumes repeating. So a pattern of these order arrangements repeating after every disordered arrangement of atoms. So this way the polymer chain is partly amorphous and partly crystalline, and that's why crystallinity therefore will range between 0% to 95%. 0% is purely amorphous polymer. 95% means there is 5% amorphous and 95% orderly arrangement of atoms. So you can never have 100% crystalline polymer. It is always less than 100%, leaving out 5% for the other phenomena like kinking, twisting, and several other configurations of the chain that prevent the orderly arrangement of atoms. So that's why it cannot go to 100% of crystallinity. It is restricted to 95% at the maximum. So you have semi-crystalline polymers which are similar to two-phase alloys and materials. So you have amorphous regions and crystalline regions. So this is what we call as semi-crystalline polymers. The metals are usually crystalline. Ceramics can be totally crystalline or totally non-crystalline, but and polymers can be semi-crystalline, so that they can adjust the rate, adjust the magnitude of crystallinity between 0 and 95%. So there is a significant difference between metals and ceramics. So metals are usually crystalline, and ceramics can be totally crystalline or totally non-crystalline. So you cannot adjust in one single in one single say product of ceramic both crystallinity as well as non-crystallinity. It is either fully crystalline or fully non-crystalline. It is fully crystalline or non-crystalline. Usually density of crystalline polymer is greater than the amorphous one, as chains are more closely packed together in the crystalline structure. That we have seen, because the density therefore becomes higher. The density of packing of these atoms is the maximum, because the atoms seat themselves as at the closest position with relative to the other atoms, closest stable position to the relative to the other atom. Whereas in case of amorphous chain, the atoms are spaced out not at the point of maximum stability or at the closest points, but they are so the spacing is not the minimum, it is more than the minimum spacing. So that is the reason why the density of the crystalline polymer is much higher than that of an amorphous polymer. So percentage of crystallinity can be calculated from this expression over here. So rho C into rho S minus rho A upon rho S upon rho C minus rho A. So so this is the expression for calculation, and the crystallinity depends upon the rate of cooling during solidification and chain configuration. So just like metals, see, in metals you can also get amorphous metals which are called as metallic grasses, which are made by very rapid cooling. So you don't let crystalline arrangements develop, and these crystalline arrangements are developed by not allowing enough time for crystal structures to form, right. So very rapid solidification is something that helps in making amorphous materials from metals. So similarly, rate of cooling of the polymer also has an effect on the chain configuration, and chains are randomly entangled in a viscous liquid, and they must be, so in order to assume an ordered configuration, adequate time must be allowed for chains to move and align themselves. So if you want crystalline polymer, then chains have to align themselves properly, and you need therefore an adequate time to pass. If you cool them very fast, then these chains are not going to be able to align themselves, and crystallinity is not going to develop. Now crystallinity is also not favored in polymers composed of complex repeat units like polyisoprene. We saw the polyisoprene structure earlier, polyisoprene structure somewhere here. So this is a repeat unit, and so with such repeat units, even if you have multiple chains and they align themselves, it is difficult to create a crystalline structure, right? It is very difficult to for creation of crystalline structure. Simple linear polymers like PE and PTFE, you can get crystallinity. So if the polymer is prone to crystallization, so wherever polymer has easy crystallization, then even if the cooling rate is high, still it will not form amorphous polymer. Even a high cooling rate is enough. It needs a very short period of time for the chains to align themselves and make an ordered arrangement of atoms. However, some polymers like polyisoprene are inherently difficult to align themselves, and therefore they take a much longer time to align themselves, and therefore even at a slow cooling rate, they are likely to remain amorphous, polyisoprene type of chains. Networked and cross-linked polymers are mostly amorphous, and because they prevent rearrangements, because once they are cross-linked, there is no possibility of any kind of movement. So the cross-linked polymers do not form any kind of regular arrangement of atoms, but then they are cross-linked, the chains are cross-linked, and therefore they derive from the strength from the cross-linking of these polymeric chains. And so the alignment to the crystal structure is therefore much smaller in case of networked and cross-linked polymers. Isotactic and syndiotactic polymers are easy to crystallize. Now crystallization or any ordered arrangement of atoms, requires some symmetry, some ordered arrangement of atoms in the polymeric chains themselves. So if you have isotactic or syndiotactic arrangement of polymer chains, then you will have symmetry in the arrangement of the functional groups, as a result of which the alignment between of these functional groups in the two chains will become easier because of the symmetry that is present, and then they will be easier to crystallize. On the other hand, atactic polymers will not have this symmetry, and due to lack of symmetry, the two polymer chains will be difficult to align, and therefore difficult to make an orderly arrangement of atoms. So that's why they will be difficult to crystallize. Random and graft copolymers are usually amorphous. So here let's see that structure again. So these are random. This is a random arrangement of polymer and copolymer, and and this is the graft structure. So this is the one polymer, and the copolymer is, let's say, grafted onto the main polymer. So these two types of random and graft copolymers are usually amorphous, because it is very difficult to again align these this chain and the corresponding units on the other chain. There is nothing like a corresponding unit, because everything is randomly arranged. So there is no way that you can bring one functional group closer to the corresponding functional group in the other chain and create a aligned orderly atomic structure. Whereas so similarly here also you have a block structure, you have a graft structure where this particular polymer and this copolymer, so this is fully polymer, this is fully copolymer, and again it is very difficult to align these. Whereas if you have a definite pattern like alternating, you have alternating polymer and copolymer, chains with alternating polymer and copolymer. If I have two chains with alternating groups of this kind, let's say you have styrene and butadiene, for example, they alternate with each other in both the chains, it is possible for me to align them, and then it forms similar to a crystalline structure. So you can have a crystalline polymer there. Similarly, if it's a block, if it's a regular block, 4 or 5 atoms of one, 5 of other etc. So now you have this polymeric chain which has been generated with a definite repeating patterns of each of these constituent chain configurations. So then when two chains have to come together and they have to arrange themselves in a regular array of atoms, it becomes easier because everything is blockwise defined, and blockwise arrangement or alignment also becomes very practicable and simple. So that is the reason why it is easy to make graft copolymers with alternating and block type of arrangements or block type of repeat units as compared to random and graft type of repeat units. Now we calculate the percent crystallinity of polyethylene. So if you have two chains which have come together, it's a good idea to calculate the percentage crystallinity of the two. So you have calculate the percentage crystallinity of branched polyethylene of density 0.925 gram per cc, while that of totally amorphous polyethylene is 0.87 gram per cc. So you have rho equal to N into A upon Vc, that is volume of the cell divided by Na. So now if you were to arrange these polyethylene in a crystalline form, then you will need to form a unit cell. So the same fundamentals as we applied from our crystal structure in metals are being applied here. So you have the density as N into A is Avogadro number, and Vc is the volume of the cell. Sorry, A is the atomic weight, and Na is the Avogadro number of atoms. Vc is the cell volume. So A is the repeat unit molecular weight. So just as in case of metals, A stands for atomic weight, here it is repeat unit molecular weight, because that is the one that has got status of an atom. So this is a repeat unit molecular weight. N is the number of repeat units. So just like you have N atoms per unit cell, similarly you have N is the number of repeat units in a unit cell, that is N equal to 2 over here. Why is N equal to 2? That is because you have I mean in the structure that is shown, you have two repeat units, and so you have A is equal to 2 into AC plus 4 into AH, right? So that gives us the total molecular weight, okay, the total molecular weight. So 2 into 12.01 gram per mole plus 4 into 1.008 gram per mole. So that is the and that gives us 28.05 gram per mole. Now we have so the density is given by 2 repeat units per cell into the atomic actually not atomic weight, molecular weight of the repeat unit divided by the volume of the cell. So volume of the cell is being given as 0.255 into 10 to the power minus 8 into 0.741 into 10 to the power minus 8 into 0.494. So that is the volume of the unit cell that we are looking at here. You see the volume of the unit cell, and you have so in the volume of in this particular volume of the unit cell, you have just 2 repeat units which are present. So that is the reason why we have written two repeat units. Okay, and so the density is 0.9998 gram per cc. So this is the Avogadro number as usual. So what is different from our calculation pertaining to metals is that instead of having number of atoms per unit cell, you are talking about number of repeat units per unit cell, and then you instead of taking the atomic weight, that is molar atomic weight, you take the atomic weight of the unit cell, repeat unit cell. Okay, the repeat units, one single repeat unit in a cell. So that you take the atomic weight of that a single repeat unit. So that is divided by the volume of the unit cell. So the percentage crystallinity here works out as follows. So rho is the rho C, that is the rho based on the cell, which is 0.998. Rho S is the branch, that is the density of the chain. So 0.925 gram per cc, and 0.87 is the density of totally amorphous polyethylene. So the density here is slightly higher than the amorphous density here. So it had been completely amorphous, the density would have been 0.87 gram per cc, but anything higher than 0.87 gram per cc therefore indicates that there is some crystallinity that is present in the material. And so based on this we find that it is 46.4% crystalline. So the polymer is 46.4% crystalline. So this is the orthorhombic cell unit containing 2 ethylene repeat units. So you have C2H2, C2H2 2 repeat units, 1 and 2, right. So inside the cell you have 2 C2H2 repeat units. So now how does it influence the properties? Crystalline polymers are stronger obviously because they are much denser, they are more closely packed and less prone to softening by heat, less prone to dissolution. Crystalline polymers are usually opaque. That is because the crystal boundaries. So when you have a crystal, naturally every crystal has its boundaries, and therefore the crystal boundaries or the planes of crystals are differently packed in different directions again, and therefore most of the crystalline polymers are opaque in nature. Whereas if you want a transparent sheet or transparent polymer, then it has to be amorphous to the extent possible. So most of the polymers which are used in for transparency applications, they are mostly amorphous in nature. Semi-crystalline polymers consist of small crystalline regions which are called as crystallites, and each having a precise alignment which is interspersed with amorphous regions composed of randomly oriented molecules. So these randomly oriented molecules are the ones which give rise to the transparent regions, whereas the crystalline regions will give rise to opaque regions. So one can generate these kinds of regions for I mean deliberately. One can, I mean wherever properties required are relatively superior, that is the product should not distort, then it should not soften by heat, it should be strong, so it should have some resistance to deformation, resistance to wear and tear. So there you would have crystalline polymers crystallizing, whereas wherever you need, for example, you take a refrigerator. Refrigerator has got a vegetable basket. Now if you want to have the vegetables visible through the polymer basket, certain regions will have to be transparent, but you cannot afford to have everything amorphous everywhere. So in the regions where greater strength is required, greater stiffness of the vegetable basket is required, you would have the crystalline polymer there. You would allow the polymer to crystallize there. That is because you need more strength, less propensity to soften or get attacked by chemicals. So basically where you need the very high properties, much greater structural strength as we call it, you would prefer crystalline setting. So, in the same product you have part of the product which is crystalline, part of the product is amorphous. As a result, part of the product is transparent, part of the product is opaque, but it is much mechanically stronger, structurally stronger as compared to the transparent regions. So, this is how you can tailor the properties you want depending on the crystallinity that you might have obtained in different regions. So, this is a chain folded structure which results in a platelet or lamellar crystallite. So, this is the lamellar crystallite, and as you see, the orderly arrangement of atoms therefore is purely obtained by folding of the chain practically in an endless manner. Now, the crystalline structure as we saw in the previous case is a straight chain polymer being bent several times and then arranged in a regular fashion. But then you can also have spherulite type of structures which forms in bulk polymers crystallized from a melt. So, if you have bulk polymers like polyethylene, polypropylene and something like that, then you will have a spherulite and it will have a semi-crystalline structure. So, part of the spherulite will be opaque, part of it will be transparent. So, it has got an aggregate of ribbon like chain folded crystallites or lamellae. So, these are the lamellae. So, these are the opaque lamellae which are approximately 10 nanometers thick that radiate outwards from a single nucleation site. So, this is a single nucleation site and these lamellae move outwards in various directions. And so, these lamellae therefore appear as thin white lines as it is shown over here. So, chain folded lamellar crystals are separated by amorphous material. So, if you take this previous case, this is separated by amorphous material. Okay. Similarly, here also you have amorphous material in between the orderly arrangement of atoms, meaning the lamellar structure chain. So, here you have the orderly arrangement of atoms due to ribbon like chain folded crystallites or lamellae, and so the same thing looks something like this as well. So this is particular what we saw here is for a spherulite structure of polyethylene. So, this is for polyethylene where you get these lamellar structures going out. So, now if you take the effect of temperature, we have been saying that crystalline polymers soften with more difficulty as compared to amorphous polymers, and again the crystals, not only crystal structure but the chain configuration also influences the rate at which the softening will take place. So, amorphous polymers will soften the fastest and to the maximum extent, whereas the crystalline polymers soften to the least extent. So, at a molecular level, as the temperature is raised, the secondary bonding forces are diminished, because secondary bonding forces are van der Waals forces, and so these are all diminished. Only the forces due to the covalent bonding between the atoms only remains behind, and that also becomes a little weaker, and therefore there is some amount of expansion in the material. So there are basically volume changes taking place as a result. So secondary bonding forces are lost, and then there is a relative movement of adjacent chains that is facilitated due to the stress applied. So if you take a polymer and heat it up, then it is very easy to deform it. That is because now that the van der Waals forces or secondary forces have got weakened, then the chains can slide with respect to each other very easily, more easily, and therefore they can deform very easily. However, irreversible degradation results when a molten thermoplastic polymer is raised to a too high a temperature, and that is because these bonds, the bonds which define the chain, the backbone bonds which define the chain, the covalent bond, they tend to break at too high a temperature. So at relatively lower temperatures, van der Waals forces diminish, and therefore the polymer is able to deform, and the chains are able to move with respect to each other. But if the heat is too much, if the temperature is too high, then the bonds between two carbon atoms, the backbone bonds tend to break, and therefore there is irreversible degradation of the polymer. That is what I had talked about yesterday when I said that if you subject the polymer to too many recycling operations, or leave it in a heated condition for a long period of time, or subject it to a lot of heat, excessive amount of heat, then the polymer degrades into smaller molecular units. So you may start with a polymer with a large molecular weight, which will have lot of strength, it will have lots of good properties, the melting point will be very high. But after you have either subjected to several cycles or left it at high temperatures for a certain duration of time, then these chains break up into smaller chains, and therefore you no longer have the macromolecule or the large sized polymeric chain that you have earlier, and therefore this irreversible degradation will take place when the molten thermoplastic is left at high temperature. So this becomes very important when you use it in a injection molding machine. So usually these polymers are used in injection molding machine, and there if the time of residence, the so called time of residence inside the heated cylinder or barrel is too high, then the polymer degradation will take place, and this degraded polymer, if added to a fresh polymer, will spoil the properties of the fresh polymer, because for a fresh polymer you will need polymer of certain atomic weight, but then this degraded polymer would have a distribution of very low atomic weights, and that will pull down the properties of the fresh polymer which you might have planned to use. Plus, thermoplastics inherently are relatively soft because they don't have too many cross-linking, as in case of thermosets. Thermosets are like fully cross-linked, and therefore there is no room for any atom to move. So either they are there or they are in a broken condition. There is nothing like a deformed condition, right? So that is why the thermosets are hard, while thermoplastics are relatively soft because of the possibility of chains moving with respect to each other. So chains can also be flexible, due to which which also contributes to the softness of the thermoplastics. So if you look at the temperatures, let's say you have a relatively low temperature, then the polymeric chains are practically fixed, they are frozen. So they don't move with respect to each other, and because the temperature is too low for them to move. So that is what happens at low temperatures. So it behaves like any metal where Hooke's law is followed. The stress, the elastic stress and elastic strain are proportional to each other, and the elastic strain of course is always fully recoverable. Then if you start heating the material, then what happens is the as I said, van der Waals forces or secondary forces break up, and the material becomes softer, and finally beyond the temperature it becomes rubbery. So this transition from a material from a solid hard material like glass to a rubbery state is called as the glass transition temperature. Okay, after that you have glass transition temperatures. So that is what is seen over here. Now what you see here is the relaxation module, because what happens is you after it has become rubbery and here it is said to be leathery in between as the strength degrades. So now here in the rubbery state, you have partly characteristics of the solid state below the glass transition temperature, and partly the viscous state of the liquid which occurs above the rubbery state. So if you go on heating it and cross this rubbery state also, then you will have viscous flow of the polymer. It will tend to melt. So you have molten polymer which is viscous. There are chains, polymeric chains floating there, and these chains generally are randomly floating and they are randomly arranged with respect to each other. So when you do a injection molding type of process, when you extrude the material in a liquid form, or you inject the material molten polymer in a liquid form, these chains which are present randomly oriented in a liquid form, they tend to get aligned. That is because you are passing them through a very narrow channel. You are trying to press them together, bring them together, and then it and the material flows, the molten polymer flows as a bunch of chains getting into the mold cavity or whatever you might want to inject that polymer into. So you have viscous flowing liquid at one end. So you know that these polymeric chains are pseudo-plastic in nature, meaning that as the strain rate increases, as you increase the rate of flow, the rate of the speed of flow, the viscosity comes down. As the speed of flow is less, the viscosity increases. Okay, so these are shear thinning materials. So what we call it as shear thinning, because if the shear rate during flow increases, then the viscosity decreases. So that is what we call a shear thinning material. So these polymeric chains which are present in the molten liquid impart the property of shear thinning to the molten liquid. In between, as the temperature goes down, the property of the solid mass of polymer and partly the property of viscous property of the liquid, so it's called a viscoelastic property of liquid. So both these properties come together, and that is the rubbery state that we see. So the viscoelastic state is found in the rubbery structure, and in a glassy state, so it is perfectly hard. It follows the Hooke's law, and so once the temperature rises above the glass transition temperature, then you see that there is a sudden drop in the modulus of the material. Now, what is relaxation modulus? Now, this relaxation modulus is typical to polymers. It doesn't exist in metals. It exists only in polymers, and the reason being is the two mechanisms, the two mechanisms which operate, namely the viscous mechanism and the solid, the interatomic attraction between the two chains, or intermolecular attraction between the two chains. So both these parameters operate together. So if you look at the relaxation modulus, what happens is that when you take the material to a particular strain and then you leave it at that for some time, there is a relaxation in the load. So if you normally apply a load, you apply a certain amount of strain and then leave the material for some time in that strained condition, then gradually it will start relaxing, meaning that the load will tend to come down. So this is typical of a viscous type of flow. One of the characteristics of viscous type of flow is imparted here. In case of metals, you don't have any viscous flow, due to which you have you always have Hooke's law being followed. Even if you increase the temperature, the equilibrium spacing between the atoms increases, and therefore the there is a linear expansion, the slope of the equipotential curve decreases, and therefore the Young's modulus tends to also come down. So the material becomes more compliant, right? So the rigidity is or the Young's modulus of metal with temperature, it tends to come down, but it does not have the changeover from it doesn't have a relaxation modulus as such, because if you at high temperature deform a metal to a certain strain and hold it at that for a long period of time, there is no time dependent variation in the load. Okay, in metals there is no time dependent variation in the load, but in case of polymers it is there, because you are talking about polymeric chains. Okay, and these polymeric chains, once the van der Waals forces have got weakened, their interactions have two characteristics. One is that of a solid glassy state, and that of viscous liquid flow, and that is the reason why if you apply a certain load, bring the material to a certain strain and leave it with time, there is a time dependent decrease in the load, unlike metal. So this is called as relaxation modulus. Okay, so this E10 is refers to the relaxation, ER10 refers to relaxation modulus at certain amount of strain, and so this stress is going to relax. So the strain is the same, but now as the temperature increases, the stress is relaxing. Okay, in case of metals, what will happen? In case of metals, what will happen? If you have held the metal to a certain amount of strain, okay, if you have held the metal to a certain amount of strain, it will tend to get into the plastic regime, because the shear strength of the material comes down, the material tends to soften, and then there is no time dependent change in the load. So what I am trying to drive at is a time dependent change in the load. So that time dependent change in the load is a property of viscous flow, and that gets incorporated into the into a polymer, and not in it is not found in metals. So you have this relaxation modulus which will come down over here. So and at the point of melting you have practically zero relaxation modulus over here. So you have different temperatures marked over here, glass transition temperature. So you have the from glassy state to rubbery state. So what you do is you mark the temperature at which it is 50% transformed from glassy to rubbery. So that is the point taken to be glass transition temperature. So now here the temperature in this case is 100 degrees centigrade. So if you look at the mechanical behavior corresponding to a certain load application, let's say you apply instantaneous load, hold it for a while, and then bring it down. Okay, whether it is metals or polymer below glass transition, it will follow the same pattern. Like the stress will rise, and therefore the strain will also rise. So this the instantaneous application of load will result in instantaneous rise of stress, and therefore instantaneous rise of strain, because now here you are talking about a behavior that is very similar to metals. Hooke's law is being followed, and therefore there is an instantaneous rise in the strain with instantaneous rise in the stress. Then you hold it in position, that is also fine. With time the load remains the same, the stress remains the same, and then when you bring it back to its to the original load value, or maybe a zero load value, then there is an instantaneous decrease in the strain. So this is the response, elastic strain response below glass transition temperature. So the behavior between a polymer and metal is similar in nature below glass transition. However, after the glass transition temperature, you have a completely different picture. So after the glass transition temperature, what happens is that the increase in load is not instantaneous. You have applied the load instantaneously, but the strain lags behind the load. So the development of strain is not instantaneous as it was earlier. It is now lagging behind the load. So actually it should have gone up straight away. It should have gone up as a vertical line, but that doesn't happen. Now it is the same thing is taking place over a large amount of time, and therefore there is a lag between the strain and stress. So now you have removed the load, and again it doesn't come back to its original, just like it came back to its original strain or zero strain. If original strain was 0, it doesn't come down to its position of original strain. It again has got viscous effects delaying that. So again the response of the material to change in load is delayed. So there is a phase lag or time lag between the load rising or stress change and the change in the strain. So that is something which is very crucial here. And then in case of fully viscous response, you have this type of a curve where strain is directly proportional to the time. So you have the so again there is a lag, but then here it is non-linear change, here there is a linear change. So if you look at the tensile behavior, we see that in case of a glassy type of state, the Young's modulus is very high, and then the material will break over here. It will not flow in a plastic manner. When you in B, it is the material is able to flow. The chains are polymeric chains, get displaced with respect to each other, and in C, it is actual polymer behavior, which is shown over here. So the yield point in case of the tensile behavior is shown like here. Yield point is determined like that. Now, unlike the metal, where work hardening takes place immediately after yielding, that is the stress rises with strain after yielding. Here it softens, the stress comes down. That is because the chains, polymeric chains tend to open up, they tend to open up, meaning uncoil or unbend, right, or untwist, and therefore there is a rapid increase in the strain and at a much lower load. So once the material has reached the yield point, these things happen very fast. And then here you see that there is a final breakage at a slightly higher stress than the yield stress, and so that's how you measure the properties of the material. Now, in case of metals, you have uniform deformation, you have neck formation here. Now, neck formation in case of polymer has started much earlier, very early, but then there is a significant amount of viscoplastic deformation taking place because the viscous effects take over. The local increase in the deformation velocity, which here will therefore result in a strengthening of this viscous area, and therefore you will have a greater elongation at a relatively lower load. So this deformation is in the presence of or a localization of strain. So if you have viscous effects, they tend to equalize the strain everywhere. Similar, now you see the properties of PMMA with temperature. You see that at 4 degrees centigrade, the stress rises very rapidly. It behaves like in a glassy state. At 20 degrees centigrade, the Young's modulus is the same, but then it is able to deform a little more. And then at 60 degrees centigrade, it gets to deform at a much lower load, meaning the viscous effects have become much stronger. We will continue our discussion pertaining to the mechanical behavior in the next class, but then we summarize saying that molecular weights of high polymers for high polymers may be in excess of 1,000,000, and then the chain length, molecular entanglements. So these are the ones which result in the mechanical behavior. Rotational flexibility, if it is diminished, then the material tends to behave hard. Thermosetting polymers, once they have hardened, will not soften upon heating because they have undergone a chemical reaction. The cross linking is a chemical reaction, a permanent change in the chemical nature of the polymer itself, and therefore there is no way that the structures can be the strain can be retrieved, or they can soften on heating. Now if there is no chemical change being undergone by the material, as in case of thermoplastics, then the internal atomic attractions, chain structure, etc., will play a role in deciding the mechanical behavior. But then if there has been a chemical change in the polymer, as in case of thermosetting polymers, then that is the one, the chemical change resulting in cross-linking determines all properties that we see. So there is no question of softening, there is no question of any ductility, there is no question of any movement of chains relative to each other. So we stop here and continue our discussion in the subsequent class. Thank you.